All right, so this is a file that is on Blackboard. I just want to go over some examples with this. Okay, so this is called, this is all from chapter 1. We did some conversions and we had a couple of equations. Here's our first equation. The speed of light is equal to distance divided by time. The speed of light is always represented by the symbol c. Its value is 3 times 10 to the 8th meters per second, or you could write it as 3 times 10 to the 5th kilometers per second. All right, depending on the circumstances, it might be better to use it that way. All right, so here are the conversions. We've certainly done some of these, but I wanted to do a few more. 1 degree, remember, can be represented this way. 1 with a little circle above it is the equivalent of 60 arc minutes. Arc minute can be, you can actually write out arc minute, or you use a single hash mark for arc minute. So 1 arc minute, remember that's the limit at which the human eye can see by itself. You can break down 1 arc minute into 60 equal parts called arc seconds. Okay, so 1 arc minute is 60 arc seconds. So another way of writing arc seconds is 60 with 2 hash marks. All right, so we get to our first formula. This is called the parallax formula. So if you know the parallax, that's what P is, and you measure the baseline, then you can measure the distance to objects. We're going to actually have a lab, if you haven't had the lab yet, on measuring parallax. You'll definitely do that, but we'll do an example or so, and then here's the last equation is, and it's actually very similar to the parallax equation. It says the diameter of something. So I'm using a capital D is so it's pi over 180 times the distance to the object times the angular size of the object. And so the angular size would be like, if you imagine, for example, like the example I use in class is, think about a chair, right? So a chair has a certain, physical diameter from one side of the chair to the other. But if you were to take the chair and move it away from you, it would look smaller, right? So that's this thing called angular diameter. Actually, that's an example that we'll use right now, as a matter of fact. All right. So what we're going to do is we're going to here. Let's switch to this real quick. We're going to prove that the moon has a diameter. So I just Googled this of approximately 3,474.8 kilometers. All right, so we're going to show that, and all we really need to know is the distance to the moon, right? And of course we're going to use this equation right here. All right, so let's do this example. All right, so I'm setting this up now. We let's say we measured the distance, or somebody measured the distance to the moon. So this is just an approximate figure here. Let's say the moon was 384,000 kilometers away. So what would be capital D with the diameter of the moon? So the thing that you need, the only thing that we need as besides the distance to the moon, is what's called alpha. All right, so alpha is the angular size of the moon. It's just we often will use Greek letters for angles. So alpha is, let's say it's, you're looking up at the full moon. So the full moon turns out to be about, so I'm gonna say approximately, all right? So we'll make it exact in just a second. Approximately half a degree, all right? So 1/2 of a degree. All right. Just so that's approximately. But suppose you used a telescope and you wanted it a little bit more precise than that, and in the telescope you measured it down to to the arc minute. And so suppose you found that it was exactly 31 arc minutes in size. All right, so given that, what we need is to find the distance. Find the diameter of the moon. We've got all the information that we need. We know the distance, we know the angle. However, the one thing that we do need to do, a half a degree, it's actually almost 30 arc minutes. If you remember the conversion, but the angle alpha has to be in degrees. All right, so let's do a quick conversion between this. So of course, we look up our conversion factor. We know that there's 60 arc minutes. The one hash mark means arc minutes in 1 degree. All right, so it's almost a half. Here, let me get my calculator here. Let's get it so you guys can see that. All right, hopefully you can see that now. All right, so 31 divided by 60. So it's a little more. I'm going to round it to 3 places past the decimal. Okay, so it would be 0.51, and see it's repeating 6 after that. So it would be 0.517. All right, so 0.517 degrees. All right, so that's important that it's in degrees right now. All right, so now we're ready to put it into our formula for the diameter. All right, so here, let's get just to that right now. So here's our formula. It's pi over 180 times the distance in kilometers in this case. Whatever the distance is in, that's what the diameter is going to be. So since the distance is in kilometers, the diameter is going to be in kilometers times the angle in degrees. All right, so let's get our calculator, which I just had a moment ago. There it is. So there's our calculator. Notice I already have the unrounded 0.51666, right? All right, so I'm just going to take that and say multiplied by our distance to the moon, which is 384,000. That's just an approximation. Kilometers, and then notice then you have to multiply by pi, so then times pi, and then divided by 180, divided by 180. All right, and notice this is it comes out to be from this calculation. Here, let me move this over here. So it's this one comes out to be 3,400 and. So let's do this. 3,462 point. I think it was 0.7. Hold on, let me look at it again, real quick. 0.7. Yeah, that's fine. We can round it to 1 place past the decimal. Remember, these problems always in Blackboard. It'll tell you how many, and of course this is in kilometers. In Blackboard, it'll tell you how rounded to this many places past the decimal. In this case, it would say 1 place past the decimal. And of course, remember, that's relatively close to the accepted value that we started the problem with. There it is, right? So there it is. I just Googled this. The diameter of the moon is right there. And then, of course, here's our calculation. Not too bad at all. All right, so let's do another example. All right, so keep in mind, in this one we did a conversion between arc minutes and degrees. All right, and we also used our formula for the diameter of something. All right, so we're going to do another problem. This time we're going to use the parallax. And now I'm writing this a little bit differently just to give us a little bit more experience. So here's the parallax. It's 0.7 degrees and 45 arc minutes and 52 arc seconds. So that's the way that that's written. I'll explain all that. We'll do a conversion in just a second. and the baseline is 5,500 kilometers. All right, if that's the information that we have, how far away is this? All right, so we're going to work this out. Of course, we're going to use this formula right here. Oops, not this one. This formula right here. That the distance is going to equal 180 over pi times the baseline divided by the parallax, and of course the parallax has to be in degrees. All right, and we use these two conversions. 1 degree is 60 arc minutes. 1 arc minute is 60 arc seconds. All right, so let's get back to this problem and let's do some conversions. Let's do the conversions first. All right, so we're going to convert this. This is one angle. Okay, so everybody understand that. This is one angle. So how do we convert that? All right, so it's, of course, it's got to be in degrees. So the first part is really simple. It's just, 0.7. All right, so that's already in degrees. All right, so we'll take it, that's supposed to be a little circle right there, sorry. And then we add 45 arc minutes, and we do a quick conversion, all right? So we know that in 1 degree, there are 60 arc minutes, all right? So the arc minutes would cancel, and then and that would change it into degrees, plus 52 arc seconds. But of course, we know that there are 60 arc seconds. Oops, that's double hash mark. There are 60 arc seconds in an arc minute, but there's also there's also 60 arc minutes in a degree. All right, so the degree would come up here, degree, or I should have used a little circle thing. But the idea here is that you just take the 45, you divide it by 60, and you add that to 52 divided by 60 squared. All right, so let's do that problem real quick. And I think I might have already done it. Let's see, let's look at my calculator. Oh, well, here, I'll do it right now. All right, so this is the angle, 0.7 plus 45 divided by 60. All right, so it's going to do the multiplication and division first, and then plus 52 divided by 60 squared. Right? So and that's just a very small fraction, right? So there's our angle. I'm going to round it to 2 places past the decimal. So the angle is 1.46 degrees. All right. So that's what this is. It's 1.46 degrees. All right. And that's really all. That's what I need. So in other words, this is the same as this. All right. This thing here where it's degrees, minutes, arc minutes, and arc seconds. Astronomy does that sometimes. So anyhow, this is the baseline right here, and this is 1.46 degrees. All right. So that's pretty much what we need. I'm going to set up the rest of it. All right. So here's the equation. With the numbers in it. There's the baseline, which was given to us. This is the angle, completely in degrees of the parallax. So of course, here's the formula again. I just wanted to rewrite that. So when you punch it into your calculator, you get, here, let me just show you. So I did this over here. Let me scoot it over here. So when you punch it into your calculator, you get a distance of 215,840 and I'm rounding it to 2 places past the decimal, 0.27, right? So it's 265, so I'd round that up. All right, so that is how you do a parallax problem. Okay, so this would be something like, you saw something, maybe a satellite or something like that was going around Earth. I mean, that's a reasonable distance for a satellite around Earth, 200 and something, 215,000 kilometers away. Perfectly fine. All right, so that is